Ladies and gentlemen, if I could have your attention, thank you very much indeed, and a very warm welcome indeed to students and staff of the Department of Materials at Imperial College London, colleagues from other departments, friends, alumni as well. It's great to have you here on this annual occasion, the fifth time now that we've had a Bowerman lecture. I should begin by saying that we have not arranged any fire drills during the lecture, so if the alarm should sound, then please make your way in an orderly fashion, either through the exits at the back or to both sides here. Make your way outside and to the muster points, and we'll be told what to do from then on. Now, this Bowerman lecture is named after Hilary Bowerman, who was one of the first 7 students who entered the Government School of Mines in 1851, and he very kindly left a bequest to the department, which actually funds this activity today. And there were some conditions on that bequest, some terms that he put in, and one of the things that he said was an acceptable use of his money was for the delivery of lectures on special subjects not forming part of the regular teaching course of the college. But he did add a caveat in that he said, provided that such special subjects shall be, in the opinion of the trustees, of prominent educational interest, and that such lectures shall not be mere festival or ornamental rhetorical exercise. So with that, I will hand neatly over to Professor Molly Stevens, who's going to chair this afternoon's lecture and introduce our speaker. Molly.
Thank you, Peter. So welcome to the festival. That's not a festival. This is going to be a wonderful lecture from Nicola. So as many of you will know, and you'll have been to past Bowerman lectures, this is really one of our most special times of the year to gather as a department and really celebrate material science in all of its different ways with a fantastic outside speaker. Now, we really try and vary the background of the speakers that come through to reflect the diversity that we have in our department. And I'm delighted that Nicola was put forward by the theory and simulation bit of the department as their preferred choice, I think by a million miles. You were the sort of outstanding choice. And so I was really, really delighted when we invited her and she was able to accept. I actually met her for the first time a few months ago when we were both in Washington for the National Academy of Engineering inauguration, but I'd been a fan of hers for years and years, so I'm really delighted that she could come. So Nicola studied her undergraduate at Cambridge, and then she did a PhD at the University of Berkeley, and then a postdoc at Yale, and then she started her first academic position at UC Santa Barbara. And was there for a while, and then I was headhunted, I expect, and returned to ETH Zurich, returned to Europe to ETH Zurich, which is also a really wonderful place to be able to do multidisciplinary research and very cutting-edge research. So she's been there since, and she's been recognized by far too many awards for me to list. But just as an example, she's obviously a Fellow of the Royal Society and has won the L'Oréal UNESCO Women's Award and many, many other awards as well. So she has all those fantastic credentials to her name, but is also actually a really warm person and very, very well liked within her community, which I think says as much as all the academic achievements as well. So we're really delighted to have you here, Nicola, and thank you so much for joining us. Thank you.
Thanks a lot, Molly, for that very kind introduction. It's really a pleasure to be here to help you celebrate in your department festival. Although now I'm feeling super intimidated that I have to not go on rhetorical, particularly because what was it?
Not ornamental.
Not ornamental. Okay. Didn't they also say not too long-winded? You left that bit out, I think. He told me beforehand also I should be not too long-winded. So now I worry a little bit about the start of my talk, because I want to start by asking you to think about what you associate with the term civilization. And I hope this is not too rhetorical or ornamental. Any thoughts? When you think of the term civilization, what comes to mind? Everyone's very quiet. So maybe for some of you, it's great museums or libraries or the arts and culture or great public buildings, leading universities, functioning systems of government. No comment. But I'm going to argue, though, in the next 45 minutes, that civilization is really just a reflection of the state of progress in material science and engineering. And in fact, you know this is the case because from the Stone Age to the Bronze Age to the Iron Age, every major advance in human civilization was driven by a development in materials. So, for example, the transition from hunter-gathering to permanent settlements was enabled by the ability to process stone. And from permanent settlements to urban centers by the processing of bronze, and to countries and empires by the ability to process iron. And so not just material scientists recognize that the course of human civilization is set by our work, but also historians and social scientists are the people who chose to name the eras of human development after the materials that dominated at their time. Today, of course, we often say that we're living in the Silicon Age. One hears that term a lot, because silicon is at the core of the microelectronics that enables much of our modern way of life. Not just computers, of course, but all transportation, communications, all technologies are either based on or heavily call upon silicon microelectronics. And over the last decades, we've improved the capabilities of silicon-based microelectronic devices to really an astonishing extent, and enabling, for example, the transition from clunky old desktop computers that some of us remember to very sleek smartphones with tremendous capability, all based basically on the same material, all with silicon at their core. And we've really become used collectively to this continued increase in capability and decrease in size and cost that's captured by Moore's law. In fact, much of our kind of economic models rely on the fact that things will get faster and better and cheaper exponentially. But as you all also know, this silicon revolution will soon be forced to come to an end, because we're starting to run into really fundamental limitations of how we can, of continued miniaturization of silicon-based devices. Eventually we get down to the size of a few atoms, and our paradigm for making a silicon-based transistor can't continue. And so this steady march towards faster, smaller, lighter, cheaper microelectronics can't continue, at least within the existing paradigm. Now you might think, does that really matter? Certainly I can't see my cell phone anymore without reading glasses on, so a smaller one is not going to help me. But it actually will pose a profound problem for society. And that's because worldwide use of microelectronics and information technologies is expanding so rapidly that if we stay with the same kinds of technologies, it's projected by some estimates that within a decade or so, half of all of our energy consumption will be taken up by information technologies. So of course this is a projection, but even if we continue to follow Moore's law, the fact that we're worldwide using so much more information technologies, this is annual IT energy consumption projected per year, even if we continue to follow Moore's law to 2025, we start to be using far too high a percentage of the world's energy for information technologies. And if we don't come up with entirely new device paradigms, and really very quickly, this is a completely unsustainable situation. So we need to hop off this silicon-based evolution and take a step beyond the silicon age. We need to have a new kinds of device paradigms for microelectronics and information technologies. And to do that, of course, we need a new material. And for all of us here in this room, this is our job, to figure out how to get off this line and get onto this line. So the story that I want to tell you today is about a class of materials that are my personal favorites, that I've been involved in the development of. And I want to tell you kind of a little bit historically for the sake of the students, to give you a kind of picture of how new kind of types of materials, new functionalities kind of evolve. And so I'll take you back to 20 years ago, maybe a little bit more than 20 years ago, when I was a young, very young, in fact, postdoctoral researcher at Yale University, and I was working on ferromagnetic materials, so materials with magnetic dipoles, with north and south poles. And I chose to work in a group that was expert in ferroelectric materials. As you know, these are materials with electric dipoles made of positive and negative charges. And my plan, or the plan of myself and my postdoctoral advisor, Karen Rabe, had been to take the tools and techniques that Karen had been developing to study ferroelectric materials and to apply them to the study of ferromagnetic materials. I'm sure you've learned in your classes about the phenomenology of ferromagnets and ferroelectrics, and the similarity in the name, the ferro in the naming, reflects the similar phenomenological behavior between the two types of materials. But what I noticed was the kinds of materials that I was studying, typical ferromagnets, for example, iron might be, I don't know if you have a favorite ferromagnet, but typical kind of black, shiny metals, typical magnets, were very different from typical ferroelectric materials. This is a picture of crystals of barium titanate, which would be a prototypical ferroelectric. So my materials were black metals. The materials of my colleagues were transparent ceramics, largely. And there were no materials that fell into both classes, or we couldn't think of any materials that were simultaneously ferromagnetic and ferroelectric. And so this seemed strange. So I went home one weekend. This was before the days of being able to do an internet search for ferromagnetic ferroelectrics. I went home one weekend with the only textbook at the time, Lines and Glass, on ferroelectric materials, and a great big 6-volume handbook of ferromagnetic materials, and looked through them both, trying to find a material that was in both of these books. And there were basically none. There were a couple of mentions of that this might perhaps be a good idea, but no substantial materials. And this question, that why there are no magnetic ferroelectrics, really annoyed me. That it became kind of, I'd like to say a passion, but it was probably more an obsession to try to figure out why the kinds of materials that were good magnets were a completely orthogonal set to those that were good ferroelectrics. So when I started soon after my own independent position at UC Santa Barbara, I basically threw away my carefully crafted research plan and decided I wanted to figure out why there are so few magnetic ferroelectrics. So this is a cartoon I really liked from the graphic artist at Science Magazine of me flying away over the beach at UC Santa Barbara on a little bubble of ferroic dipoles. So we worked for some years on this question with a combination of computational studies, so electronic structure calculations using density functional theory that I know many of you are expert in, and also a lot of paper and pencil, basic phenomenology, and eventually we're able to understand why there are so few magnetic ferroelectrics, and also to propose routes to getting around the contraindication between ferromagnetism and ferroelectricity. And what we found was really very simple, and now it seems really trivial, actually. And that's that the kinds of chemistries, the kinds of elements, the arrangement of the valence electrons in atoms that are good for making ferroelectrics is different, or ferromagnets, sorry, these are the magnetic ones, is different from those that are good at making ferroelectrics. They sit in different parts of the periodic table, and the way that they engage in chemical bonding is different. So for the experts, atoms that are, or magnetism comes from unpaired electrons from the spins not canceling out, and this is found in atoms that have partially filled d orbitals, which sit kind of in the middle of the transition metals in the periodic table. To be ferroelectric, an atom has to move off-center. It has to create an electric dipole by not being surrounded evenly by other atoms, and this is favored particularly by atoms that have empty d orbitals that are over to the left of the transition metals in the periodic table, because then they have space available to make chemical bonds. So this was a very simple discovery. At the start of this study, we thought, maybe there's some real basic physics reason, like some fundamental symmetry reason why ferromagnets break time reversal symmetry, ferroelectrics break space inversion symmetry, why they're not allowed to be combined. Turned out this is not the case. It's really just this simple chemistry. And so understanding this, then it was very encouraging. We were then able to make materials that really were, at the same time, both ferromagnetic with their magnetic dipole and ferroelectric with their electric dipole. And we called these multiferroic because they have multi kinds of ferroic order. And there are now very many extremely clever ways of making multiferroics. Most of the clever ways I did not work on. They were done by other people. The routes that we took were very simple, and I'll talk about those. And the simplest one was basically just by combining the chemistries, by making compounds that contained both the atoms that are good at being magnetic and the atoms that are good at being ferroelectric, at making electric dipoles. And here the prototype is bismuth ferrite, bismuth iron oxide, which is a perovskite structure in which the magnetism comes from the iron, from the fact that the iron has a very large magnetic dipole moment. And the ferroelectricity in this case comes from the bismuth, which is good at making an electric dipole because it has a lone pair of electrons that can make an electric dipole. So this was our first route to making a really good multiferroic. Bismuth ferrite existed previously, but its properties, it had not been made in a form at which its multiferroic properties could be established. And really the breakthrough, I'd say, we were not smarter than people who tried to do this before. We just tried to do it at a time when the quality of the materials that could be prepared was such that the intrinsic properties could be measured. So here's a high-resolution transmission electron micrograph from Marta Rossel, who's now at EMPA in Zurich, of a film grown by the group of Ramesh at UC Berkeley. And you can see the white dots here are the bismuth atoms. Maybe you can just about see the iron atoms also. And I'm showing you this to show you that this is a really perfect thin film. And so the state of thin film growth had evolved to the stage where we were able to produce these materials and really measure that they were multiferroic. So that was our first pathway to making multiferroic materials, just combining the chemistry that gives good magnetism with the chemistry that gives good ferroelectricity. Our second approach was a little bit, maybe a little bit cleverer, and that was by making unusual crystal structures in which one could trick the magnetic atoms into making electric dipoles, even when they don't really want to, by virtue of the crystal structure. And here the example that I'll talk about a little bit more later is yttrium manganite. When you look at this chemical formula, probably you all think perovskite. Those of you who recently had a ceramics class, it's a typical chemical formula for a perovskite structure. But you can see it's not perovskite. It has layers of yttrium atoms separating layers of trigonally bipyramidally coordinated manganese, MnO5 trigonal bipyramids that are corner shared. And so this unusual structure leads to electric dipoles, even in spite of the fact that the manganese is magnetic. So this was a second approach. And again, these materials existed, but not in good enough quality samples to be able to reveal their multiferroic properties. And so in this case, we were able to make rather beautiful single crystals using floating zone. This is a quite large half a centimeter crystal grown by my colleague Frank Lichtenberg. And you can see, yeah, it's a very beautiful crystal. It looks black. It looks like a metal. It's actually not. It's a rather good ceramic, but it has quite a narrow band gap, and that's why it has this black color, but it's actually a very brittle ceramic material. Okay, so this was quite some effort and many years' work to be able to make these materials that are simultaneously magnetic, ferromagnetic and ferroelectric. You might be thinking, well, okay, why would we really want to do that? Why should we be motivated to have materials that are magnetic and ferroelectric? And the main motivation at the start, well, I won't lie. My main motivation was this was really fun. I thought this was a really interesting fundamental research challenge. But the motivation that we sold to the funding agencies was, oh, this is being recorded. Okay, we can maybe 20 minutes in, we'll cut out cut out that comment. The technological driver was electric field control of magnetism. So magnetic materials, I talked earlier about silicon being the core of all of our contemporary microelectronics, but complementary to silicon in many devices are magnetic materials for storing the data. So where silicon is used for processing the data, it's kind of the thinking part, the magnetic materials are the memory. They're used for storing the data. And they do this in the opposite orientations of the dipoles, representing the ones and zeros of digital electronics. So here's a magnetic force micrograph of actually kind of now old-fashioned hard drive. You see the opposite orientations of the magnetic dipoles, which tell you whether you have a 1 or a 0 stored in your memory device. And magnetic materials are extremely good at this. There are, of course, other technologies also, but these magnetic data bits, they can be very stable, they can be very small, and they can be detected very easily. Above a magnetic data bit, there's a magnetic field that lets me easily detect whether I have a 1 or a 0. So this is a very, very good technology. But magnetic storage has one downside, and that's that it's usually controlled. Magnetic data bits are controlled using magnetic fields. So if I want to write a magnetic data bit, if I want to reverse the orientation of one of these dipoles, so I want to write something different, so I don't just get stuck with the last student's thesis, I can write another one, then I need a magnetic field in order to do this. And you all know how to make a magnetic field. You need a coil of wire, and you need to run a current through it, and that can be quite a big, bulky component, and it heats up, so it uses a lot of energy. So making a magnetic field is energetically an unfavorable process. But imagine if we had instead a multiferroic material that, along with the magnetic dipole, we had an electric dipole. So now, as well as the north-souths, I have a plus-minus associated with the magnetic dipoles. Then I should be able to control the magnetic data bits, but using an electric field. And to make an electric field, you all know this as well, I just need 2 little electrodes and a very, very small amount of energy. So electric field control of magnetism has the potential for huge reduction in the amount of energy associated with magnetic data storage because we can control the magnetism electrically. So this was the next big question for us after we'd achieved, after we had some multiferroic materials, was can we then control the magnetism using an electric field? So I'm going to show you the very first data where we were able to demonstrate this in collaboration with the group of Ramesh at Berkeley, because it's to show you quite how bad the data was at first. So it didn't start with this beautiful high degree of control, but it was extremely exciting. So this is the very, very first demonstration in a multiferroic where we were able, with an electric field, to control the magnetism. So this is these are images, again, of bismuth ferrite. So this is the first multiferroic that I told you about, in which the magnetism is coming from the iron, the ferroelectricity is coming from the bismuth. And these are images of the same area before I do anything to them, before there's any electric field applied. And the top image is taken using a technique called piezo force microscopy, which is sensitive to the ferroelectric domains. So in the top image, the black and white regions are electric dipoles pointing out of the page or pointing into the page. In the bottom image, this is, again, it's the same region, but imaged using a technique called photoemission electron microscopy, PEM, and this is sensitive to the magnetic domains. So in this case, the black and the gray correspond to magnetic domains pointing out or in to the screen. And what's the first thing that you notice about these two images? They're basically the same, right? So this is extremely encouraging that there's some correspondence. If we look at this kind of funny little shape here, this kind of dagger shape, it's also down here. This triangle is up here, and so on. So before we do anything, we see that there's some kind of correspondence between the electric and the magnetic domains, which of course is important if we want them to be talking to each other. So then we apply an electric field to this material, and the electric field, of course, will affect the ferroelectric domains. The electric field will couple directly to the electric dipoles and reorient them. And what you see is that the pattern changes. When I said this data is very primitive, you see that it doesn't change at this stage very systematically, right? But it certainly changes. And now we have a different arrangement of electric dipoles after we apply an electric field. Now, what happens to the magnetic dipoles, the magnetic domains? Again, you see that when I change the electric dipoles with an electric field, the magnetic domains change to follow. So this kind of pointy triangle here is reflected here. This strip here is up there. And so particularly, let's say I focus on one region here that goes from white to black. Then down here, it goes from black to white. So this was super exciting for us. It may not, I don't know if it looks so exciting to you all now, but we were extremely, extremely excited about this. With an electric field, we could reorient the ferroelectric domains, and the magnetic domains followed. This was picked up also, I think it was not just us that were excited. It was in the Breakthrough of the Year section at the end of 2007. That physicists used electric fields to manipulate magnetic domains in a multiferroic, and success could pave the way for chips that combine the logic functions of semiconductors with the memory functions by magnetic materials. I was super excited about this because we were in the same issue of the Science Breakthroughs of the Year as the Large Hadron Collider. Although I had to admit, even at the time, that I was kind of more excited about the Large Hadron Collider. But it was anyway pretty exciting. I want to show you this also to give you an idea of the timeline. So we first started thinking about multiferroics kind of in the late 90s, started really to understand what the issues were in 2000, had the first materials about 2003, and then the first demonstration of electric field control of magnetism in 2007. So it took about 10 years, I say, from the concept of, oh, it would be nice to do this, to being able to do something that's even demonstrating that it could be potentially useful. And last year, the first prototype multiferroic devices were announced from Intel. I was a little disappointed. Actually, they published their device in Nature, which to me probably says they're not really convinced that this is going to be a really good technology, because otherwise they may not have published it. But it's better than nothing, I guess. Oh. Okay, I want to show you one more example of how multiferroics could be relevant for microelectronic devices. And I'm sure I chose this example a little bit because I wanted to introduce this image, which is from my colleague Manfred Fiebig, who also at the ETH. This is again, a piezo force microscopy image. So this is showing the ferroelectric domains, the plus and minus oppositely oriented electric dipoles, in the other multiferroic that I introduced at the start, in yttrium manganite. And well, two things about this. The first thing is it's just strikingly beautiful. I think Manfred should sell this to Gucci or something as a fabric pattern. And the other is that it's really unusual. Any of you who are used to looking at ferroelectric domains, usually they're like stripes or a kind of tweed pattern, but this kind of pattern is extremely unusual. Always kind of six-fold. You see there's always black, white in sixes meeting at points. It's very unusual. And this is a result of the unusual crystal structure that, because of its, that also allows for the multiferroicity. So if you like, this crystal structure, this ferroelectric domain structure is not a consequence of the multiferroicity. The unusual crystal structure results in this ferroelectric domain structure and in the multiferroicity. And this particular image, the polarization direction is in the plane, and the black and white are corresponding to electric dipoles up and down in the plane. And so if you think about this for a little while, so here's a blow-up of one particular region. In this region here, say, the ferroelectric polarization might be up, and in this region here, it might be down. And here's a high-resolution microscopy image again. This is not from our group, but the group of Zhang and co-workers. This is this domain wall, this intersection between these up and down regions of polarization. You can see it's a very sharp interface, and the up polarization is marked by a kind of up-up-down pattern of the yttrium ions, and the down polarization by a down-down-up pattern. So we see that there's a change from up to down at that line. If you think about this for a moment, electrostatically, this is a very unhappy domain wall, right? Here I have a dipole pointing up with its negative charge at the bottom, and here I have a dipole pointing down with its negative charge at the top. And in this region here, basically my system would explode, right, if it was forced to stay like this. It doesn't explode. What it does is it adjusts itself to screen this two negative charges being pushed together. And in this picture, this is again a picture of the same domain structure using a technique called conductive atomic force microscopy, which tells us how many carriers, how many electrons or holes are in the sample as a function, spatially. It's a spatial map of the number of carriers. The arrows are the polarization again that are measured using piezo force microscopy. And at this region here, where I have the tail-to-tail wall, the bright coloration in the conducting atomic force microscopy is telling me I have an accumulation of carriers. In this case, this material is slightly native p-type. All the holes go here to screen the negative charge, and I have a conducting channel that's angstrom thick and can be moved around with an electric field. So this, I'm not a device physicist, I can't tell you what you should do with that, but if there are any device physicists in the audience, it seems to me that it's a super interesting capability to have an angstrom-thin conducting unit that can be controlled by electric fields. So this is an idea for other possible, or a material functionality that could lead to other possible device applications. At the head-to-head wall, there's no electrons, free electrons in this system, so the holes deplete, and it makes a net negative charge by getting rid of the holes, and so there's a depression of the conductivity, as you would expect. Okay, so maybe we're about to enter a multiferroics age, or maybe some age determined by some other material that one of you is developing or will be developing in the future. I think it's a big open question what will happen in microelectronics technology after silicon. So, of course, there's a lot more to life, hopefully, than microelectronics, and a lot more to material science than information technologies. And particularly all of you students, I encourage you to think about the research that you're doing, how it's relevant for meeting the United Nations Sustainable Development Goals. And I think it's really hard to find any research in material science and engineering that is not contributing to answering one of these questions, actually. So any electronic materials-based research that might result in more efficient devices is undoubtedly contributing to issues of affordable energy and climate action. Reducing energy needs is essential for solving both of these issues. Clean water and sanitation and life below water, anything that is promoting water purification, for example, is contributing to this. And I want to show you a couple of other examples from multiferroics related to these other United Nations goals that I had nothing to do with, but I think are really interesting. And they're interesting to me because they rely on the kind of opposite functionality of multiferroics. They rely on magnetic field control of the electrical properties, which was not something we even had in mind that this might be useful at the start of our work in this direction, but it's proving to be an interesting concept. So this is work on water purification from my colleague Salvador Pane at the ETH. And Salvador has been able to demonstrate that nanorods, nanoparticles of bismuth ferrite, can take large, nasty organic molecules. This is a rhodamine B molecule. And when they're shaken using magnetic fields, they can break down these nasty molecules into little molecules like water and ammonia. And the mechanism here is really interesting, or the mechanism we believe is occurring, is that one has a bismuth ferrite particle, and one side of it is it's ferroelectric, so one side of it is negatively charged and the other side is positively charged. And so water or oxygen will adsorb on these charges to screen the surface charges. Then with a magnetic field, or alternating magnetic field, the electric polarization is changed and the surface charge changes. And so this causes the molecules to dissociate and form radicals where they're then able to break down the organic pollutants. So it's kind of a similar mechanism to photocatalysis, except for instead of having the photo with a magnetic field, you're breaking down the water. So this is an extremely beautiful work, I think. Another example which is contributing to human health and good health and well-being, which again, it was completely surprised me that a multiferroic could be useful for this, is bone tissue generation. So certainly I start to think of things like new knees are going to be a good thing sometime in the not too distant future. And with aging populations, tissue regeneration starts to become more and more of an issue. And it turns out that, of course, bone, as you know, is piezoelectric. And it's believed that in the human body that this piezoelectric property of bone might be helpful for bone regeneration. If you have an injury, you can't be banging your bone against the ground to make piezoelectric, to actuate the piezoelectricity. But what you can do is apply a magnetic field. And a magnetic field, of course, can be applied remotely outside of the human body. It doesn't need electrodes. And so it's more desirable for biomedical applications to address magnetically than electrically. And so what Salvador has been able to show, this is not in vivo, this is still in vitro, is that a scaffold with bismuth ferrite nanoparticles under application of a magnetic field promotes the growth of bone osteoblasts. So a couple of directions that at the start of our work we had absolutely no idea would be possible technology outcomes, but have proved really quite interesting just because we were able to generate materials that had really new functionality. So one maybe shouldn't always be thinking only of one goal in mind, but also of just generating materials that do new things. And then somebody else really smart might find something to do with them. I feel I've a little bit been focusing, I don't want you to give the impression that all my research that I do is useful. So I'm going to finish with an example of multiferroics research, which is really, really not useful, but I think really, really fun. And I'll stop in 5 or 10 minutes so I don't violate the rule of going on, I can't remember what the phrase was, going on for too long. So this is back to this beautiful yttrium manganite picture. And I want us to look at these intersection points where I have always 6 ferroelectric domains coming together. So this is a cross-section of the surface, and these, of course, look like points. But in 3 dimensions, they're lines. These actually form strings running through the sample in 3 dimensions. And so I need to give you a small quiz. One of these boxes is a computer simulation from Thomas Lottermauser and the group of Manfred Fiebig of exactly these strings in the multiferroic, the strings forming the intersections between the ferroelectric domains. The other one is a simulation from Martin Kunz at the University of Geneva of the formation of cosmic strings, which are textures that are proposed to have formed in the early universe out of the primordial vacuum at 10 to the minus 37 seconds after the Big Bang. And the quiz is for you to figure out which is which. I'll give you 1 minute, maybe. And then we'll take a vote. Okay, I hate to break up the discussion, but let's have a vote. So who thinks this is the multiferroic? Oh, you can't see the pointer? The red one on the left. Who thinks the red one on the left is the cosmic strings? And who thinks they can't tell? So you're right. In fact, this was the simulation done by the multiferroics researchers. This was the simulation done by the cosmologists. But the simulation was of the same thing. So there was actually mathematically no difference in these 2 simulations. And we're going to use this analogy between the proposed mechanism for the formation of cosmic strings in the early universe and the real structural phase transition in yttrium manganite that forms these ferroelectric domains to study the proposed formation of cosmic strings using our multiferroic material. So in the last 5 minutes, I'll show you exactly how we do that. Here we go. This is the multiferroic simulation with the domains, and this is the early universe simulation. So both of these, the multiferroic material undergoes a symmetry-lowering structural phase transition that generates the defect lines. The proposal, of course, nobody knows what happens actually 10 to the minus 37 seconds after the Big Bang, but the standard model of cosmology proposes that the early universe underwent a symmetry-lowering phase transition that generated these defect lines, which are called cosmic strings. These are different than string theory cosmic strings. They're, Okay, so I'm going to give you an example of a symmetry-lowering phase transition, and kind of as an analogy, and it's not actually a very good analogy. So this is a quiz for the undergraduates to figure out, we'll discuss this over drinks later, to figure out what's wrong with this analogy. But it's not such a bad analogy, except it's kind of a bit wrong. So but it'll serve the purpose of illustrating the properties of a symmetry-lowering phase transition. So an example of a symmetry-lowering phase transition, which probably you're more familiar with than cosmic string formation or obscure multiferroics, is the water to ice phase transition. So when water is hot, of course, it's either it's liquid or vapor, and it's high symmetry. Even though it's all amorphous, it's high symmetry, because if I sit at any point and I look in any direction, I see the same disorder in every direction. As I cool it, it crystallizes into ice, and this is now lower symmetry, because now if I look up, I see the bottom of a molecule. If I look to the right, I see the side of a molecule. So I see different up and to the right, in the low symmetry phase. So this is the first feature of a symmetry-lowering phase transition, that it lowers the symmetry as a function of some parameter, in this case changing the temperature. Another feature of symmetry-lowering phase transitions is what's called defect formation. And again, the water to ice can illustrate this. And this is actually the Stockholm archipelago, and you can see that it's freezing. And so there are platelets of ice forming on the water, so the platelets of the low symmetry phase. And one region of the water may crystallize with one orientation, and another region of the water will crystallize with another orientation. And so when these regions meet together, there's a defect. In this case, it'll be a planar defect between the platelets of ice where they meet. So here's platelets which might have different orientations, and this defect formation where they meet. The last point to mention is that associated with these defects is often a functionality. And so we saw already in the case of yttrium manganite, there was a conductivity associated with these domain wall defects. In the case of the ice, the ducts, you can see, sit in the middle of the platelets because the food gets stuck at the intersections. So the functionality in this case, I guess, is algae, which are at the defects. So three properties of symmetry-lowering phase transitions. They lower the symmetry, there's defect formation, and these defects have functionality. In the case of our multiferroic yttrium manganite, we have a symmetry-lowering phase transition. It's a structural one, like the water to ice. In this case, from a high symmetry crystal structure, you see the yttriums are nice straight lines, and the MnO3 trigonally bipyramidally coordinated layers are nice straight lines. As we lower the temperature, there's a symmetry-lowering phase transition to this much more bent structure. And at the intersections between different bent regions, we form these lines, these intersections between the ferroelectric domains. Mathematically, we describe this process by a potential which has the form of a Mexican hat. So this potential is showing energy as a function of magnitude of the distortion coming away from the peak of the hat and angle of the distortion as I go around the brim. And this is not a cartoon. This is actually mathematically, when we calculate this process, this is mathematically what the energy surface looks like. The proposal for the early universe is that the early universe had nothing in it. It was a very high symmetry vacuum. As the universe expanded, there was a phase transition from high symmetry to low symmetry vacuum that was described by exactly such a Mexican hat potential. So this is a model. Don't ask me to explain how one can have a vacuum-to-vacuum phase transition, because to a materials scientist this is far too obscure or far too esoteric. But the point is that the proposal for the early universe is that it had a symmetry-lowering phase transition with the same symmetry as our yttrium manganite. And so, since we can't replay the Big Bang and measure what happened after 10 to the minus 37 seconds, we can't generate cosmic strings in the laboratory. The largest hadronic colliders that we have are about 10 orders of magnitude too weak to actually generate a cosmic string. We can look for signatures of cosmic strings in the cosmic microwave background. There are very well-defined proposals of how they should manifest in the cosmic microwave background. These have not been seen yet, so there's an upper bound on the existence of cosmic strings, the concentration of cosmic strings that's allowed. We already saw that we can make computer simulations, but what we're going to do instead is, in the laboratory with our multiferroic yttrium manganite, actually run the experiments that our cosmology friends would like to do on the early universe, but instead run these experiments on the yttrium manganite. So they would like to know, do cosmic strings exist? Did they form as we think? How did they evolve? And what are their properties? And in particular, one question that our cosmology friends would like to know is, if the early universe had expanded at different rates, how many more or fewer cosmic strings would form? And they have well-defined proposals for that, which we're able to test directly in the laboratory by cooling our multiferroic at different rates and counting how many different, line defects, how many cosmic string analogs formed in the different cases. So this is, look at the scale bar here. This is the same scale bar in each case. I didn't just take this one and blow it up, although I could have done because these are self-similar. These are samples of multiferroic yttrium manganite that have been cooled at the three most easily experimentally accessible cooling rates. One, the furnace was switched off and the sample was left in the furnace. One, the sample was put on the lab bench, and the other, the sample was dumped into liquid nitrogen. And you can see we have very measurably different concentrations of cosmic strings in these three cases. And so one can have a friendly undergraduate count these for their bachelor's project and actually study, it's a very cool bachelor's project, and study really the scaling, the dependence of the formation of cosmic strings on how quickly the universe expanded. Not at all useful, but I think for me, probably the most fun project I've ever been involved in, thinking about how can I take materials physics and start to address questions in other branches of science and engineering that don't have that are not traditionally experimental fields, that don't have access to direct measuring. So let me end with some propaganda I think some really excellent scientific journalism that was motivated by these experiments. This was an article in National Geographic that said the universe's existence may be explained by our new material. What I really like, actually, is, a new material could help physicists explain the existence of matter, such as this astronaut seen above the Earth. So there's nothing at all to do with them, anyway. I thought this was extremely creative. So I'm showing you this, of course, as a little bit of a joke, that we're not really, with our research, not really explaining the existence of the universe. Or at least not entirely, because of course what we do and what you all do as researchers is explain or work on explaining and try to explain your own corner of the universe. And so it's what defines us as scientists and engineers. And so I hope I've conveyed to you how much fun we're having trying to explain our little multiferroic corner of the universe. And I wish you all the very best in your research activities explaining your corner. Thank you very much for listening.
Thank you, Nicola. That was just so perfectly pitched. I understood a lot of it, which is a great achievement. So I mean, this was marvelous, actually, starting from the civilization, drifting very quickly over some of the politics of the day, into the, of course, wonderful science that you've been doing, some of which is really applied and actually has been built on by so many other people, which is why your work is so widely regarded, I think. And then on to the things at the end that you call not useful, but actually explaining potentially the universe. I just would also like you to explain to me where consciousness comes from. I don't know that yet. But a lot of the other big questions you've actually managed to address in your talk. So really, really a fantastic talk and a treat, I think, for everybody here. So I'm going to invite Peter up. We don't have questions after the Bauman because it's such a special annual lecture for us that we have the reception afterwards for all questions and networking. But I'm inviting Peter up to present the medal.
Yeah, so Hilary Bauman request was stretched for a medal.
Thank you very much.
Hand this over to Nicola.